Now I'd like to hand the podium over to our first keynote speaker of the event, Dr. Ken Rochford. Dr. Rochford is the CEO of SPIE, the International Society for Optics and Photonics. This is one of two major international optics societies. Probably best known for a broader group is they're the host annually of the Photonics West Conference, which we all talked about quite a bit when we had a good tech hub footprint there. Prior to his role at SPIE, he was an associate director for laboratory programs at the National Institute for Standards and Technology. He also served as the acting NIST director in 2017. This was a capstone of a long and prestigious career at NIST, rising through the ranks. Dr. Rochford holds a PhD in optical sciences from the University of Arizona and an MBA from the University of Colorado. He spent some time in industry in between stints at NIST and has worked at kind of big multinational companies, startup companies. So he has a good range of experience that kind of lines up with what we're doing. He's going to talk to us today about kind of where optics and photonics are kind of at the cutting edge and how it really impacts us across society. So let's give Kent a warm welcome.
All right, thank you, Tim, and good morning. Let's see, I'm guessing left, right, cool. All right, I'm gonna talk about photonics, my favorite thing to talk about. I'm gonna talk a bit about technology, but it's gonna be tech light. There's only gonna be one equation. It's one that you all know, and I've actually written down some stuff to ensure I don't use acronyms. So I'm going to start with a little bit about SPIE. I think a lot of you know what we do, but I think a little context is helpful because at the end I'll talk about how we hope to be able to support the Tech Hub. We're a professional society, have almost 25,000 members, and we support the optics and photonics community. So we hold conferences and trade shows around the world, and we bring researchers, engineers, industry together, and they give presentations. All that content, the posters, the presentations, the papers, end up in a huge digital library that we have. So that technical content's available to all. And we support scholarly publishing and education as well. We do a lot of short courses. We also support the community through scholarships, grants, and activities. A lot of student chapter work, student travel funding. And we also do advocacy. The purpose of the advocacy is to raise awareness for the importance of optics and photonics. And as an example, we've created an optics and photonics congressional caucus in which your Senator Dane serves as a co-chair. So, what's this thing called photonics? Broadly defined, photonics concerns the generation, manipulation, and detection of light. So, for centuries, optics was this field that was looking at, the properties of light and how you could kind of move it around with prisms and lenses, and essentially was focused on imaging, things like cameras and telescopes. But with the discovery of lasers, and then with the observation of some really interesting novel interactions between light and matter, and then the ability over the last several decades to engineer materials, to engineer complex devices, this technology space just exploded, well beyond optics, and the term photonics was coined, being analogous to electronics. Electronics, we all know that word, right? It's how you move electrons around to do cool stuff. Same thing, we're just using photons. So today, we now create light through LEDs, lasers, organic materials, quantum dots, and more importantly, we can actually engineer all the properties of these light emissions. We developed a rich technology set that can modify each of these properties. So it's things like polarization, wavelength, and more exotic things like coherence and entanglement. And we can do this to remarkable effect. And we are now in the position where we can detect each of these properties from way more than megawatts down to single photons. So the toolbox of photonics is pretty amazing. And as a consequence, photonics has become indispensable. I mean, it entertains us, it illuminates our spaces, it keeps us healthy, it supports our security. It's ubiquitous. It's used in a vast range of technologies and applications. And because of this breadth and depth, it's now seen as a critical enabling technology that underpins most of what we do. I mean, frankly, our modern society, the way we live our lives today, would not be possible without this technology. And it's everywhere. So, I'm going to use this smartphone example because it's a great example of the pervasiveness. Globally, there are more active mobile phone lines than people on the planet. These phones are everywhere. And the phones are loaded with photonics. There's things you can see. There's cameras, there's a display, there's sensors, there's lights, there's even LiDAR in the newer devices. And inside, there's semiconductor chips. And they simply could not be manufactured without photonics. And it's not just semiconductor manufacturing that requires photonics. Photonics has now become a key part of many manufacturing lines. It's used for cutting, welding, patterning, drilling, inspecting, and sorting. And back to our smartphone example, at least 10 different laser processes are used in several dozen steps to create basically this everyday device. Now, your phone isn't useful in isolation, and photonics underpins that ability to communicate. So wireless RF and microwaves, it's enabled fantastic mobility, right? We can walk around anywhere and communicate. But we're not just talking on phones like we used to. We're transferring data, lots and lots of data. And as you aggregate this data from hundreds and thousands of phones, you eventually require capacities that cannot be served through copper wire. And you end up requiring optical fiber to transport this data to the central office, between central offices, and to route that traffic to other destinations. And from this data, we just don't want numbers. We expect instantaneous information. We want search results, streaming video with high definition, gaming with low latency, all of which comes from data centers that are bigger than several football fields. They're jam-packed with servers, and all of that's created and connected by photonics. So when you use your phone to do a Google search or look at a Facebook page or get an Amazon shopping list, that request is going to aggregate data from dozens of servers throughout a server farm. And that requires very high data rate optical links between the servers, from the server to the rack, from the rack to the router, and from the router out. And because one data center doesn't hold everything, photonics is required to link the United States and the world together through fiber optic backbones and submarine cables. So the aggregate worldwide installed internet bandwidth enabled by photonics at this backbone is 1.2 petabits per second. That's 1 with 15 zeros. That's 1 million gigabits per second. That's enough capacity to transmit every written work in every language ever done by humans since we started writing in a couple minutes. I mean, these are vast amounts of capacity. And you couldn't do this without photonics. I mean, wires are just too lossy at high data rates and over distances. Microwaves are too constrained, and you need this. And it's growing, right? Our data needs are not decreasing. They just keep growing. With AI, it's going to explode. So the R&D in this area is actually mind-boggling. The most recent HERO experiment achieved about a quarter of this capacity, 300 terabits per second in the lab, by packing almost 1,100 different wavelengths, each carrying 250 gigabits per second onto a single fiber. So we're in this incredible rich technology space. And there's so much more. I mean, right now, we're in a world where very complex and novel parts can be made by sintering metal powder with a very precise pattern written by laser beams. That's just then lifted down another layer of powder, and it's repeated. And through that, you can build up 3D parts that have complex shapes that can't be machined using normal techniques. Solar panels now generate about 5% of global electricity. And that's an area where we're still working to make those panels cheaper and more efficient. Directed energy weapons, they've actually now been demonstrated, and they're starting to be deployed. There's going to be more work in that field. And mixed reality, AR, VR, is providing new ways to visualize, new ways to discover, and new ways to learn. So photonics is clearly important. But what's the photonics industry? So, if I say semiconductor industry, everyone knows what I mean, right? It's Intel inside. If you're paying attention to AI, you probably know what NVIDIA is. And everyone's seen a picture of a fab. Automotive industry, no problem. There's cars, there's manufacturing lines, maybe Detroit, if you're my age. But because photonics is enabling and ubiquitous, it's hard to pinpoint, what this photonics industry is. So it's an enabling technology. It's not a simple delineated industry. Industries are basically categorized by what's called a NAICS code, North American Industry Classification System. There's no NAICS code for photonics. There's no real formal designation, so the industry isn't readily recognized. In fact, the companies that we at SPIE believe are photonics companies are having to use over 200 different NAICS codes to self-identify. So there's really no simple fit. But being an enabling technology actually has a huge advantage. Photonics can address a wide breadth of applications and markets. And that provides great business opportunity and also some degree of resilience for those that are diversified. I mean, I see career paths where people can move from application to industry readily because that toolbox of photonics is so widely available or widely useful. And we also benefit from this great wealth of methods and technologies. So we have a field that's able to provide a variety of solutions to many problems. The demand for photonic solutions continues, and it's supported by R&D in a field that frankly has a lot left to learn and a lot left to discover. So we're well positioned for innovation. Now, despite these challenges with NAICS codes, we do try to quantify our industry, and we publish our results in our global industry report. So to make this tractable, we work on what we call we focus on what we call the business of core photonics. So these are the building blocks. This is laser diodes, lenses, optical fibers, imaging arrays, the simple building blocks that generate, manipulate, and detect light, and then enable this vast ecosystem that I alluded to. Right now, we're tracking over 4,700 companies over 4,700 companies over 50 countries. And because we use a repeatable and routinized process, it also gives us the ability to track trend information. So to summarize the highlight of our report, global core photonics market, it's robust and it's growing. We report nearly $370 billion in 2020 global revenues in this just component level sector. And moreover, it's been growing steadily with an annualized growth rate of over 7% over the 10 years that we've studied. And we've seen revenue double over this 10-year period. Industry employment is also growing, and we now support 1.2 million workers worldwide. It's worth noting that the core photonics market has outpaced the global GDP for the decade we've been tracking. This field is growing at almost 2.5 times the rate of global economic expansion. Now, we rely on retrospective data to do our report. We're looking at public reports, but we also monitor guidance from larger companies. And from that, we can forecast that core component revenues going to reach about $400 billion this year. So that implies growth in every of the 12-year periods that we've tracked. In my job, I also have the opportunity to meet with executives from various companies. And the consensus is continued growth through 2025, with particular strength in semiconductor industry, particularly in the last half of this year, in defense, in medical sectors. There's growing interest in quantum development. And basically, so even key decision makers from the industry side have a pretty positive outlook as well. Now, our industry report also includes estimates along this value chain. Tomatis, a European market analyst, released a report last week, and it reports $865 billion for product and subassembly level. So that's the core components, plus some electronics and software to actually have, something that can be put into a product. And that about doubles the component value. I'd mentioned the report was released last week. They also forecast continuing growth that also outpaces worldwide GDP, reaching $1 trillion in 2025. Now, going up the value chain, the photonics-enabled products serve a variety of sectors, more of the breadth that I'd mentioned. And here the value nearly triples to $2.4 trillion for these photonics-enabled products. That's things like, smartphones, lighting system, semiconductor tools, sensors for autonomy, sensors for security, communications, things of that ilk. And when we break that down, consumer, defense, and displays, along with biomedical, account for about 75% of that impact. But none of these products in these sectors we count could exist without photonics. Now, one thing I'd like to draw your attention to is this 4.3 compound annual growth rate for photonics-enabled product. It's higher than the worldwide GDP growth, again, showing above trend demand. But that's actually lower than the 7.3 growth rate we're also seeing for core components. And what that means is the core components, the most basic part of photonics, is actually a growing share of the content and the value of really, to me, reinforcing the importance of photonics. So ultimately, photonics now enables this vast business in services as well. Things like video streaming, cloud computing, e-commerce, and that's a major driver of the economy. Rough measures of that suggest that our ecosystem supports services valued at $16 trillion around the world. That's 15% of all global economic activity. Again, underscoring the reach and the importance of what photonics does. This economic footprint is the result of really remarkable innovation. And I think it's fair to claim that photonics is a major technology driver. Since the laser was invented in 1960, photonics has made growing contributions. And here is a proxy of breakthroughs considering Nobel Physics Prizes. Since 2000, half of all Nobel Physics Prizes were for directly a breakthrough in photonics or were a breakthrough that required photonics to achieve that groundbreaking result. If you go to labs in almost any industry or any sector around the world, instruments, measurements, and tools enabled by photonics are widely used by researchers in many fields. And this photonics-based innovation is accelerating. Arguably, one of the most celebrated, if not most impactful, Nobel laureate invoked the speed of light to develop his theory of relativity that showed how the passage of time is affected by gravity, and that mass and energy are equivalent by this famous equation. Einstein was awarded his Nobel Prize 102 years ago. It wasn't for relativity. It wasn't for this equation. It was for his description of the photoelectric effect, where he demonstrated that light has the property of quantized energy, work that led to the concept of the photon and to photonics. So, sorry we missed the celebration. Just as recently as a few years ago, the impact of all this was recognized by the United Nations, and UNESCO's declared May 16th, the date the laser was first demonstrated, as the International Day of Light. So that's our celebration. It was Thursday. Sorry I wasn't here to celebrate with you. But if you are interested in more things that photonics can do and what careers might look like, dayoflight.org has a lot of that information. So I encourage you to take a look. So what's next for photonics? Continued innovation across the board. Basically, any technology sector you can imagine is going to continue to be impacted by photonics. But as an umbrella, sensing is incredibly important, which makes this tech hub very relevant and very timely. So in the next few slides, I'm just going to talk about a few sensing innovations. I have the benefit that I'm able to go to conferences around the world and pop in and hear talks. So I get to see some of the new cool ideas that people are doing. And it's interesting to see. So for example, a lot of people don't realize this, but most healthcare testing, most biological laboratory instrumentation, it's photonics based. Couldn't do it without it. You remember Theranos? That was called bogus technology. But the idea that you can take a small sample of blood, have it react with biomarkers in a low-cost cartridge, and use a little device to do a fast point-of-care measurement, that actually exists. There's a company called LightDeck that does this. They do some small protein panels, testing panels. They've actually moved into water contamination. And it works because they're able to do very specific tuned wavelengths very highly tuned, high precision, and very sensitive photonics in a throwaway cartridge that uses bioanalysis. I've seen this at conferences, and some of this is actually being used. Photonic sensing can be used in real time for identification that aids surgery. So there's more to light than what we can see with our eyes, and there's more to tissue than what's just reflected. Advanced techniques like spectral analysis, things called Raman scattering, where you interact light with matter, things like optical tomography, where you can actually get into some depth of matter. They reveal this wide variety of tissue characteristics that researchers have correlated with disease. So the system on the left is used with endoscopes. So often endoscopy is being used to take biopsies. Well, when you do biopsy, you're essentially kind of doing a random sample. So it's hit or miss. People have used Raman scattering in a probe that they can then use to kind of look at the sample and determine whether it's at high risk of disease or low risk of disease, and then let the surgeon pluck the biopsies from the higher risk to actually improve, the ability to do diagnostics. The system on the right is also depicting a probe that's being used to delineate parts of tissue in the brain. And that allows the neurosurgeon to actually find the tumor margin, where the tumor actually is. You generally can't see that by eye. So the typical technique is cut, biopsy, go back and cut, microscope biopsy, and repeat. And that often leads to not taking out all the tumor or taking out too much. And in brain surgery, really don't want to take out too much. So this is a tool that they're now using to actually maximize the removal of malignancies while preserving as much healthy tissue as possible. So, sensing can be used in a variety of ways. LiDAR is this great tool that that is an acronym, sorry. Everyone knows what LiDAR is, though. It's providing a rich data set. It's being used in things as diverse as construction, where people can get as-built drawings, they can do estimating, they can understand demolition better, retrofitting. It plays a large role in spatial awareness, functionality, which helps with robotics, helps with manufacturing. These are very accurate and precise measurements, and it's led to some interesting use cases. One thing I've actually seen working is people using LiDAR to measure parts of the human body to help fit prosthetics. There's a group that's using this to figure out what parts of the skull might need to be replaced during after an injury. They can take that LiDAR map, put it into a design tool, feed that into an additive manufacturing where the laser 2D printing makes a bespoke stainless steel or metal titanium piece that can perfectly fit that missing skull. And all this stuff is becoming somewhat cost-effective, actually quite cost-effective. And as they become more compact and readily available, the applications are almost limitless. Now, I kind of alluded to semiconductors earlier. This is a picture of the most advanced photolithography tool today. This is what $250 million looks like. And with this tool, we can now pattern extreme dimensions, 8 nanometers. We're at the point where these features are a dozen or so atoms. It's pretty phenomenal what we can do. The CHIPS Act, Tim had alluded to that. That's really accelerating investment both in capacity and research. That means more sales from those of us in photonics that are creating the manufacturing tools, the testing tools, the inspection tools. But it's also going to support R&D as well with outcomes that I think will directly affect photonics. And I think one of the most interesting outcomes will be a boost for photonic integrated circuits. And those are devices that are like like semiconductor chips, but they're based on photons instead of electrons. And in the US, that benefit's gonna come from CHIPS Act investments in mature nodes, but also calls for manufacturing packaging research, R&D, and calls that are going to include photonics that are gonna come out in the next few months. The EU CHIPS Act actually specifically targets photonic integrated circuits because they're seen as a foundational technology. And we're seeing pilot lines being built in the EU to boost this technology. So picture this huge opportunity that borrows semiconductor techniques to integrate a multiple number of photonic functions. I know the keynote, I just met Kevin earlier today. He's going to give a keynote, I believe, on PIC, so I won't get into details. But I think, to me, the most interesting thing is, in the lab, we have lots of components on an optical table, and then those of us that make product put all these components into a box. When we can start integrating things on a chip, and they're compact and cheap, I mean, imagine what you can do with these things. Imagine what you could do with a LiDAR that only costs a couple dollars, right? I mean, you're just limited by your imagination at this point. It's just going to be game-changing. And it's also going to enable, I think, a lot of interesting work in quantum. So photonics has actually been well-suited for probing the quantum limits. So when we also talk about these new funding opportunities like the National Quantum Initiative, photonics has been foundational in advancing this technology. The best photonic clocks are now so accurate that if you take two of these and set them side by side, and you lift one up by a centimeter, those clocks can actually discriminate the difference in passage of time that Einstein had predicted through his theory of relativity. These clocks are so accurate that they lose a half a second in the lifetime of the universe. Now, this is just amazing technology. If you can make this compact, now you can actually do things like, because it's a super good gravity sensor, you can use it to locate underground deposits, water, minerals, oil. You can measure magnetic fields. You can find submarines. You can perform inertial navigation, so you don't need GPS, and just a host of other activities. Superconducting detectors now can count single photons with high efficiency and with no noise or dark count. And this has enabled a capability that's just mind-blowing. We can now measure stuff where photons are really sparse, like astronomy from stars very far away, or imaging through tissue, right? Tissue is, you put photons in your skin, it scatters, it gets absorbed. It turns out some of those photons will actually pass through your finger. Very, very few of them. But if you can count those and image them, you can actually understand the pathway through tissue and actually do measurements in that way. In addition, these are useful for things like entanglement in the quantum regime, and they enable quantum communications, where you're now able to send messages securely, so even they can't be eavesdropped upon. You can actually have very secure communications. So back to our friend Einstein, he was not a fan of entanglement. He derided that as spooky action at a distance. He believed that quantum mechanics was therefore incomplete, and there was something missing. There was a hidden variable that we just hadn't discovered yet. And people spent some time on that, and it wasn't until the 60s when an American physicist basically developed a test that could determine if this, if quantum mechanics was complete, or if it was just, plain weird. But to do this, you actually needed detectors of very high efficiency and low noise, which these enabled. So actually, when I was at NIST, some of the early experiments were done, and they showed that there is no hidden variable, that quantum mechanics is just weird, and this led to the Nobel Prize in 2022. And one interesting thing, this is a total aside that has nothing to do with anything, but I think it also shows how cool photonics is. To do this test, they had to use random variables to do lots of measurements. They built a random variable bit stream by taking the bit streams from videos of Star Trek, Monty Python and the Holy Grail, Back to the Future, Doctor Who. It's the only high-impact professional scholarly journal I know of that actually has in the citations all our favorite movies in it. So we get to have fun with it too. So anyway, we're now in an era where quantum sensing, communications, and quantum computing is going to make amazing, and not just scientific, they're going to make amazing economic changes that improve our life. And again, this stuff is loaded with photonics. So amazing and important, I think life-changing results are going to come from this. So I just want to close. I hope you all see that photonics is a rich technology, that thinking about sensing is actually quite timely and relevant. This is an ascendant technology. It's poised to solve real problems It's poised to create real markets, right? This isn't just a theoretical construct. This is work that's actually going to help improve lives. So congratulations on the progress on the Tech Hub. We stand ready to help. I think there are things we can do to help support this as it goes forward, and fingers crossed until the awards announced this summer. So thank you very much.